In this unit, we will talk about equilibrium and then extend it into acids and bases, especially weak acids and weak bases. As we learned in thermochemistry, whenever we study some chemicals, we can define it as a chemical system. Empirically, which means lab-based evidence, these things can be measured in temperature, pressure, volume, or the number of moles of chemicals present. It is much simpler to study equilibriums in a closed system. That is, where energy and matter cannot escape from our chemical system. If we are to study aqueous solutions in chemical systems, in that system the gas cannot be produced, or if a gas is produced, the gas must be trapped within our reaction boundaries. The simplest example of a closed system at equilibrium is the case of a can of pop or a bottle of pop. If it is unopened, it can sit there indefinitely. The carbon dioxide in solution remains in solution. However, as soon as the bottle or can is open, the carbon dioxide escapes out of the solution. We no longer have a closed system and equilibrium has been lost. In earlier courses, you learned that chemical reactions always happen 100%. That is, they always happen so that products are formed and then no reactants are left. However, in real life, this is rarely true. There is always going to be some reactants that have left. This can best be explained by using collision reaction theory. This theory states that the final state of any chemical system, or the equilibrium position, is really a result of a competition of the reactants to form products, and products reacting to form reactants. We will call the forward reactants to make products the forward reaction or the right reaction, and then the backward reaction, the formation of reactants from products, to be the reverse reaction. Here we have an example of sodium sulfate reacting with calcium chloride. The forward reaction should produce calcium sulfate and sodium chloride. Whereas the reverse reaction, where the products in this equation react in a backwards manner to form the products. For this system to hold true at equilibrium, it must be a closed system because the reactants and the products cannot escape. They must be made available to react. In our example here, notice that the arrows here are double-sided, which means that the reaction can occur both ways. Of course, the arrow that's pointing to the right is called the forward reaction, whereas the arrow pointing to the left is called the reverse reaction. Let's talk about equilibrium now. Remember, equilibrium is only for systems that are closed chemically, and an equilibrium is considered to be established when we can no longer see any macroscopic changes, so such as things like pressure, temperature, or color change. There are three types of equilibriums that we will study in this course. The first is a phase equilibrium, which is the conversion of a gas to a liquid, or a liquid to a gas, or vice versa. A solubility equilibrium, in which case a solid is dissolved into a solvent. And the last equilibrium is a chemical reaction equilibrium. This is the type of equilibrium we will study the most in Chemistry 30. All of these equilibrium are explained by a theory of dynamic equilibrium. The word dynamic means that it is always moving. That is, there is always a little bit of the forward reaction happening and a little bit of the reverse reaction happening. The key here is that those reactions happen at the same rate so that there is no overall net formation of products or reactants. As we mentioned before, the first type of equilibrium we can study is a phase equilibrium, where a system, in this case a beaker of water, is going from a liquid state to a gaseous state. Notice here the arrow is double-sided, which means that water is both going from the liquid state to a gaseous state and from a gaseous state to a liquid state. When the system is at equilibrium, the rate of those reactions will be equal to each other. The second type of equilibrium is a solubility equilibrium, where a solid is being dissolved into a solvent. The example shown here is of solid copper sulfate dissolving into copper 2 plus ion and sulfate ions. Again, the arrow here is double-sided, which means that the rate of salt dissolving is the same as the rate of precipitation. Overall, the mass of the solid copper sulfate will not change over time, even though any particular ions of copper sulfate may be dissolved into water. If one molecule of copper sulfate is dissolved into water, one other molecule of copper ion and sulfate ion will precipitate back into copper sulfate solid. The last type of equilibrium we will study is a chemical reaction equilibrium. However, this is the most complex kind because many molecules are interacting with each other. And to study chemical equilibriums, we need to combine 5 previously studied topics: the atomic theory, which states that all matter are made of atoms; kinetic molecular theory, which states that all matter are vibrating at temperatures above absolute zero; collision reaction theory, the theory that we just learned a few slides ago, which says that an equilibrium is established when reactant molecules collide to produce products, and products molecules collide and react to form reactants. The concept of reversibility, whereas any reaction is reversible. And lastly, the theory of dynamic equilibrium, which states that equilibrium is reached when the rate of forward reaction is equal to the rate of the reverse reaction. A simple system that scientists use to study equilibrium is called a hydrogen iodine model. In this model, hydrogen gas reacts with iodine gas to produce hydrogen iodine. Hydrogen and hydrogen iodine are clear, colorless gases, whereas iodine gas is a purple gas. So initially, there is an excess of hydrogen and iodine, so there is a clear purple color in the flask. However, as time passes and reactions occur, more and more hydrogen iodine molecules, which are getting colorless, form, and fewer iodine molecules remain because they have reacted with hydrogen gas to produce hydrogen iodine. So overall, the amount of iodine decreases, so the color of the flask appears to be lighter. And lastly, when equilibrium is reached, if we were to do a chemical analysis of the contents of the flask, we would find there will be amounts of both iodine gas, hydrogen gas, and hydrogen iodine. The color of the flask would remain constant over time. That is, they would have reached dynamic equilibrium. The concentrations of all 3 species do not change. We can look at the results for 3 different experiments with our hydrogen iodine system. In our first set of experiments, if we place only the reactants, hydrogen and iodine gas, into the flask and no products, at equilibrium we find that there is going to be fewer molecules of hydrogen iodine gas and much more molecules of the product, hydrogen iodine. If we place in a second system small amounts of the reactants and a moderate amount of the product, we still see formation of additional product. From that, we can know that this reaction favors the forward reaction, because we will still create additional product even though we have some product already. However, even though a reaction favors the forward reaction, or equilibrium favors a forward reaction, in our third system, when we have no reactants and all products, there is still a significant amount of the reverse reaction happening to generate a small amount of the reactants, and the overall concentration or the overall amount of products has decreased. By looking at the equilibrium system concentrations here on this side, we can also determine that this reaction favors the forward reaction because at all equilibrium conditions, there is more of the hydrogen iodide products than of the hydrogen gas or the iodide gas reactants. Chemists have determined two ways to measure the equilibrium of any chemical system. The first is the percent reaction of a system. It describes equilibrium for one specific product. The formula to determine percent reaction is the amount of the product measured at the equilibrium divided by or compared to the maximum possible yield. So in formula form, the percent reaction is amount of product actually produced divided by the amount of product that was theoretically available to be produced. And this percent yield or percent reaction can be useful to communicate the position of equilibrium, and of course how we determine the theoretical amount of product that is produced is via stoichiometry. The second way that chemists have used to describe equilibrium is what's called an equilibrium constant. Now from other courses, you'll recognize the word constant in that there is going to be a mathematical value associated with a constant. And furthermore, this equilibrium constant describes all the system of the same reaction at any one temperature. It can be used to calculate the concentration of any product or any reactant in our chemical system. We can also describe an equilibrium by using a graph. On the x-axis, we have the time or reaction progress. And on the y-axis, we have the quantity or concentration of the various species we have in our system. So in this graph, we see that initially we have a moderate amount of hydrogen gas and iodine gas and no hydrogen iodine. But over time, hydrogen iodine is produced, whereas hydrogen gas and iodine gas is slowly consumed. Now remember, in an equilibrium system, there are two reactions happening at any one time. The first is the reaction of the reactants becoming products. However, the rate or the speed of this reaction slows down as the number of molecules, reactant molecules, decreases, mainly because there are fewer reactant molecules to turn into product molecules. However, on the other hand, the rate of the reverse reaction, where the product changes back into the reactant, will increase as the number of product molecule increases. Because there are more product molecules, they are more likely to hit each other and produce a reactant molecule. Now, at some time, these two rates will become equal, and this is when dynamic equilibrium will be reached. If we go back a few slides earlier where we used percentage yield to denote the position of the equilibrium, and now we calculate the actual percentage yield of those three different systems, we find that approximately 78% of the percentage yield of the product is formed. So to communicate this, we can write the number 78 above the arrow where we can see the reaction is written. Using the percent yield or the percent reaction, we can classify any reaction into one of four categories. If the reaction yield is less than 1%, we know that the reaction favors the reactant very strongly. In fact, we can say that reaction does not happen at all. If the number is between 1 and 50%, we can say that the equilibrium is also favoring the reactant, but there is an observable forward reaction. However, if the reaction is between 50 and 100%, so the reaction percent is greater than 50%, we can say that the reaction favors the product. However, at equilibrium, we can still detect signs of the reactant. And lastly, if the percent reaction is greater than 99%, we can say this is quantitative. It reacts 100%. it will be almost impossible to detect any signs of a reactant molecule. And on this last slide, we have a table from the textbook summarizing those four values. If it's negligible, such as less than 1%, we can say the reaction is non-spontaneous. There will be no product formed at all. If the percent yield is less than 50%, the reactants are favored. If it's more than 50%, the products are favored. If it's almost 100%, it is quantitative, which means there will be no reactant molecules left at the end of the reaction.